what do you guys want to do today? Yep.
Can we do examples of the experiments, the homework that I've been working on? Like, you can learn them by definition, but it's kind of hard to see what applies to what.
See what applies to what in the...
Like, in an experiment that's like the one about smoking or something.
Okay.
You can know what all the definitions are, but then you know how it's like choose all that apply? They're kind of tough.
Talk through that a little bit. Yeah. I don't even remember which examples are in the or in the assignment. So let's open this in another. Oh, the MRI guided cingulotomy? Is that in the homework, or is that on the exam? That's the homework? Okay. That's not my email address. Oh yeah, this is a gem. So my best friend from college became a neurosurgeon. He actually died kind of unexpectedly. It'll be a year ago this coming Monday. But I occasionally go visit him. I'd flip through journals that he had on the shelf, like Journal of Neurosurgery. Or New England Journal of Medicine or whatever. And there were always some real howlers in these absolutely top-notch journals, just brutally terrible examples of how not to do an experiment, but published in a first-rate journal. So this is one of those. All right, so let's read this and talk about it a little bit. Okay, so here in the early to mid 1990s, there was an experiment done. Excuse me. At Mass General Hospital, which is a first-rate hospital, and it was looking at doing basically brain surgery to treat psychiatric disease that wasn't responding to other kinds of treatment. And basically, there were, it was a relatively small sample, which is maybe a good thing in this case, normally not. These people had all been referred by the psychiatrists who were treating them. They were reviewed by some panel that was studying this treatment. And most of the panel were actually authors of this journal article. And if the committee agreed unanimously the patient should get the procedure, and the patient consented, then and the sort of some of the things they looked at in deciding whether or not to do this surgery were, had they, they didn't respond to drugs, they didn't respond to psychotherapy, they didn't respond to behavioral therapy, and they didn't respond to electroshock. Another nice humane thing. Okay, so, and then they had to have been sick for at least a year, and they had to have what was considered a serious psychiatric disease, major affective disorder with unipolar depression, bipolar depression, developmental disorders, OCD with major depression, blah, blah, blah. Okay. And then there were some patients who were given the surgery. Some of them who didn't get better were given a second surgery, which is a wonderful medical model. If it doesn't work, do more of it, right? That's all right, so the cingulotomy procedure is basically they fry your brain. They drill some holes through your skull, and they pass radio frequency electricity, a very, very high frequency, high high voltage through the electrodes, which basically cooks a piece of your brain. And they cook it for something like 90 seconds. And in 1993, they modified the procedure so they cooked a little more of your brain. All right, so of the 34 subjects, there were 31 who were available for follow-up assessment of some kind. Of the 31, 2 had committed suicide. I mean, this is not funny, but it's funny, right? OK. The assessment was done in one of 2 ways. Either the person who had referred them to go get this treatment, or the psychiatrist who was in charge of the treatment, completed some questionnaires, or if the patient wasn't seeing anybody anymore, thank you very much anyway, they looked at the most recent correspondence with the patient and tried to assign ratings based on that, like, I'm fine, doctor, really. Okay, I'm sorry. This is horrible. I couldn't figure out. I couldn't find in the article how many patients were in each of those categories, but they basically ended up categorizing people into one of 2 categories, either a responder, or 3 categories: a responder, a possible responder, or a non-responder. All right. So 14 of the patients who hadn't responded 6 months after the initial procedure had more procedures then, and this is, kind of the summary of what happened. All right. So is this an experiment or an observational study or just a really, really sick joke? Yeah, OK. Yeah. OK, so there's nothing to compare it to. So the method of comparison is not being used, right? Does that mean that it isn't an experiment? They choose who gets the treatment. OK. So it's an experiment, but with no controls. Does that make sense? Is there any randomization? No, they're just treating the people who were referred and who they decided to treat for whatever reason. All right. Now, if you wanted to know whether this stuff worked, right, the first thing you would need to do is to compare it to something else, right? Because even if people have been sick for a year, that doesn't mean that they won't ever get better from some other treatment. And so if you somehow want to know whether it's worth cutting people's heads open and frying their brains, you might want to compare the recovery rate for this group to the recovery rate for some other group that had some less invasive treatment, like just electroshock, for instance. OK. All right. So there's going to be a problem from confounding, right? I mean, it's sort of there's no controls. You have no idea why the people who got better got better. Why was that? All right. So in particular, even if there were no direct psychological effect, direct effect on your, I mean, it's hard to believe that it doesn't affect you at all, right? But that even if it didn't affect the symptoms of your psychiatric disease, the fact that you've undergone brain surgery, you know that that happened to you, right? OK? So would you expect there to be a placebo effect? No? You know you were being treated. Yes. OK, right? So what's the idea of placebo? You give me a pill. I don't know what's in the pill. I know I'm being treated. My pain gets less. My pain decreases, even if what's in the pill is sugar, right? That's the placebo effect. Placebo effect is knowing that you're receiving treatment of some kind, whether that treatment has an intrinsic effect or not. The knowledge, the beliefs around it affect the outcome. That's the placebo effect. OK? Does it? Right? So you don't have to be given a placebo for the placebo effect to matter. The reason people are given placebos is to eliminate the confounding due to the placebo effect, so that you're comparing, so that the difference between the treatment group and the control group is not whether they got something, it's the difference between what they got, right? OK, so the placebo effect is likely to be a source of confounding here. Does that make sense to everybody? OK, because everybody knows they got brain surgery. Yep. whether or not the brain surgery actually matters. Okay, who is doing the evaluation of the subjects here? Is this a blind experiment? Is this a double-blind experiment? Neither one. Okay, so who's evaluating the people? The very same people who recommended that they get the treatment and who are putting their names on the article and taking credit for how wonderful this is when it's over, right? So would you expect that, consciously or not, there would be a tendency to interpret people's behavior, et cetera, as improvement, even if there were no real improvement, okay? All right, so this is likely to play a role, all right? Does self-selection enter here? Well, go ahead, cut me open. I'm so desperate, I'll take anything, right? Whatever, okay. All right, so people are basically, they're being proposed for this, but they're also volunteering, right? If they say no, it doesn't happen to them. So there is an aspect of self-selection, and that's likely to probably interact with the placebo effect. If you think it's likely to help, you're so desperate, you're feeling so terrible that you're willing to do this, you might be looking for any conceivable improvement at all and be, okay, so that's likely to be mixed in as well. Patients unavailable for follow-up. Is that going to be a factor here? Do you think the patients who are unavailable for follow-up, it could be that those are all people who are now so well that they're no longer in the medical system at all, right? Or it could be the other way around, right? That they're now so bad that they're not going to talk to anybody from Western medicine ever again, right? Okay. It's hard to know, but that is certainly something you might think about. Okay. Self-reporting follow-up based on last correspondence. It's just hard to know how to compare the self-reporting with the physician's reports. We might exaggerate our condition as being better, especially if we just want to be left alone. Okay, just hard to know. Improvement in your mental health unrelated to the cingulotomy. I wonder why this is, oh, it's because I stretched the page, that's why. Improvement in mental health unrelated to cingulotomy. Okay, so if you got better because of psychotherapy, not because of the cingulotomy, you wouldn't be able to tell that apart because there was no comparison to people who just got psychotherapy and not the cingulotomy, or psychiatry and not the cingulotomy. Does that make sense? Okay, all right. So a lot of these things are likely to be issues, yes? All right, if you wanted to know how effective cingulotomies are for treating this psychiatric disease, what might you want to know? All right, now, the wording of the question, this is something you want to pay attention to. Like, this is effectiveness for treating psychiatric disease. This is not safety of the procedure, right? It's a sharp question here. If you want to know, does this work to help people get better who've had a year of symptoms and aren't getting better from other things, right? So is B relevant? I'm sorry. I can zoom in and then we'll lose a little bit of the... let me see if I can do it the other way that somebody taught me how to do. What was that? This is the control. Except now I can't. Can I go sideways? I can't go sideways. All right, let's see what I can do here. Okay, I'm not going to like solve the whole problem set, but I just want to talk about some of the stuff. All right, so if you want to know how effective it is, does B matter? No, I mean, it might matter for something, but it doesn't matter for knowing whether it's effective for treating psychiatric disease. You don't really care what it does to people who don't have psychiatric disease. You're not going to do it to them, right? Okay. What about C? Exactly. So C is something to compare it to. If you want to know, does the cingulotomy help, you'd like to compare what happens with the cingulotomy to what happens without the cingulotomy. Right? So this is the idea here is this is some measure of what happens without the cingulotomy. Okay, so it would be nice to know that. Right. Okay. All right. How about this 95% confidence interval story? Is there a random sample here? No, there's no confidence interval. No random sample, no confidence interval. Right? You can calculate anything you want. It just doesn't mean anything. Okay? We would need to be doing some kind of randomization somewhere in order to come up with a confidence interval when we're done. Does this make sense to everybody? Okay. Right? What's a confidence interval supposed to do? It's supposed to say, in replications of the experiment, you're making an interval so that if you did this over and over and over again, 95% of the time in replications of the experiment, that interval would include the truth, right? The true effectiveness, okay? But here, there is no randomness to the replications. It's some particular group of people who got referred by a particular set of physicians at a particular time at a particular hospital, so forth and so on, a particular study. They weren't a random sample of people who had psychiatric illnesses that had lasted longer than a year, for instance. Right? It's just some group. That's all. That's all you know. Okay. Okay. Does that help? Yep. Okay. All right. What should we do next? Yes? How can you determine what? Effectively random? Well, I mean, if it isn't really random, it wasn't really done by rolling dice or pulling tickets out of a hat, which, by the way, isn't a good way to do randomization. I think I mentioned that. But, or using a pseudo-random number generator, then it's very difficult for something to be effectively random. John Snow's study of cholera is, the cleanest example of something that, for all intents and purposes, was random, even though it wasn't, because just the different water supply houses went, through buildings that were next door to each other. Nobody had any idea where their water was coming from, so forth and so on. It was an accident that had happened years, decades, whatever, before the study in question. It was just that's pretty darn close to random. There aren't a whole lot of other examples that I can come up with that are anywhere nearly as compelling as that. But yeah. Other stuff. Shall we? Okay, so let me just suggest some options, and you can pick or suggest something else. We could go through a practice final together. That might be worth doing. I could lecture on the next chapter, which is not going to be covered on the final, but some of you are going to want to do the problem set, or at least talk about that some. I could just answer questions in general. I'm at your disposal. I can't tell you what's on the final because I haven't written it yet. Practice exam?
Can you briefly tell us what won't be on the final?
The chapters that weren't assigned. Categorical logic won't be on the final. The ones that are sort of the extras. In general about the final, the story is I try to make it modest in length so that everybody has plenty of time to finish. Again, not that people won't stay till the end. Some people will stay to the end, but most people will not feel time pressure. This practice final that's here is the final that I gave at the end of it's one version of the final that I gave at the end of the summer, this last summer. So this is the most recent final that I've given in the class. Yep, sample 4 is the last one there. OK, just a reminder that you need to bring a Scantron to the exam. You need to bring number 2 pencils. It's the same Scantron form that we use for the midterm, the sort of oblong one that has, what, 50 questions on a side, something like that? OK. You need a number 2 pencil. You need your photo ID. We will be checking ID. OK? And you're welcome to bring a calculator. You're welcome to bring a fancy TI or HP calculator. You are not welcome to use your cell phone to do calculations or anything else that has communication ability with the outside world. Sorry? Cheat sheet, yes. 2 pages, front and back, 4 sides. 4 sides in all. Typed. Anything that you can read with your bare eyes. You're not allowed to bring in, microfiche reader to... two pages, front and back, 4 sides and all. OK. Right. Sure. I mean, it's not supposed to be about memorization, right? I mean, the fact is, the world is an open book test, right? You want to have the concepts clearly in mind. You want to know where to go to figure things out, how to think about stuff. But it doesn't matter whether you've got the formulae memorized or not, to me anyway. OK. Other general questions before we launch in? OK. So, yep. If you're on the homepage, you click on Review. Yep. Maybe I should change the title to Practice Stuff. OK. OK, so people have this notion of what random digit dialing is for a phone survey. That basically, there are, area codes are kind of fixed. Telephone exchanges are like the first 3 digits of your phone number after the area code, like 642. OK, so one of the ways of doing a phone survey is, you would dial an exchange 642 and then dial the last 4 digits at random. And some of those numbers are going to be dead numbers. And some of those numbers are going to be real numbers and have people at the end. And some of them are going to be real numbers, but nobody's going to answer, and so forth and so on. OK, so if you do random digit dialing, some people are going to among those numbers that are real numbers for that have a telephone at the other end, some people are going to answer and some people are not. And furthermore, some people that you reach are going to hang up on you, and some people are not. So there's no reason to think that the non-responders are different from the responders. Therefore, it's reasonable to conclude that non-response doesn't bias the survey. OK, is there any fallacy to that? Yes. What is the fallacy? It's an appeal to ignorance, right? Just because there's no reason to think they're different does not mean there's reason to think they're the same, right? No evidence of a difference is not evidence of no difference. All right. Here's a really tough one. Yeah, OK. A, therefore, not A. Oh, OK, yeah. What is not A? A. OK. A, therefore A, right? OK, so that's valid. OK, Yahtzee. I've never played Yahtzee. How many of you have played Yahtzee? A few. OK. OK, so my understanding of this is indirect and vague, so you can correct me if I get it wrong. In the game of Yahtzee, players roll 5 dice. There's 13 rounds per game. In each round, you can roll the dice up to 3 times. In your first roll, you roll all 5 dice. In the second and third rolls, you can choose to roll any subset of the dice or all of the dice again. Okay? And the way that you score the number, so in the end, there were sort of 5 dice showing numbers on top, right? And the way you score it is that you look at what numbers are showing on top when the person is done with his or her turn. An especially valuable roll is 5 of a kind, so if all 5 dice show the same number of spots. All right? So that's called a Yahtzee. And what's the chance that you roll a Yahtzee on the first roll of your turn? All right, what's that closest to? So how do we figure out what the chance is of rolling a Yahtzee? OK, so we have a hypothesis that it's a 6th to the 5th. OK, where's that number coming from? Sorry? But does everybody like this number? Or somebody like a different number? It's just 1/6. We have another number. Okay, I like this number. Okay, why do I like that number better? Okay, what's 1/6 to the 5th? That'd be the chance that you get all 1s, for instance. 5 1s. 5 1s is a Yahtzee. That's the chance you get 5 1s. That's the chance of that particular Yahtzee. 5 2s is also a Yahtzee. 5 3s is also a Yahtzee. 5 6s is also a Yahtzee. Right? There's 6 different mutually exclusive ways you can get a Yahtzee. Each one of them has chance 1/6 to the 5th. So in all, the chance is 6 times the 6 to the 5th. That make sense? OK. All right, so that's going to be pretty close to one of those numbers, I bet. You don't understand that? OK, so rolling a Yahtzee is getting 1 1 1 1 1, 2 2 2 2 2, 3 3 3 3 3, et cetera, on up to 6 6 6 6 6. OK, the chance of this is a 6th to the 5th. Chance of this is a 6th to the 5th. OK, all these have chance of 6 to the 5th. Any one of them is a Yahtzee. Chance of a Yahtzee is the chance that any of these things happen. They're mutually exclusive. So the chance of this or this or this or this or this is the chance of this plus the chance of this plus the chance of this plus the chance of this because they're mutually exclusive. OK? They all have the same chance. So there's just 6 things that have the same chance. We just multiply this by 6. Is that, we're all together? This is a really good time to stop me if this is confusing. This is, you know, all right. We good? OK. All right, what's the chance that in the first turn, all 5 dice show different numbers? I don't know. I just make up the questions. I don't know the answers. OK, so how can we think about figuring out what the outcome is? What has to happen to get 5 different numbers on the 5 dice? How many numbers is it possible to get? 6, right? There's 6 numbers to choose from. Yes? OK? Every dice is going to show some number, right? OK. So from the 6 possible numbers, we need to pick 5, right? And those 5 might be, for example, 1, 2, 3, 4, 5. It might be 6 that gets left out. Yep. But now, that's just saying we rolled. This is saying 1, 2, 3, 4, 5, but that 1, 2, 3, 4, 5 could be in a bunch of different orders. Could be 2, 1, 3, 4, 5. Could be 5, 4, 3, 2, 1, whatever. So we're thinking that we need to say the first die gets some number from 1 to 6. This is saying the first die got number 1. Second die gets some number from 1 to 6. We're saying the second die showed 2 spots on top, et cetera. Okay? So how many ways are there of assigning these 5 numbers to the 5 different dice that we rolled? 5 factorial, right? Okay. So what we've got now is for any particular set of 5 numbers, there's 5 factorial orders that they could be in. When we're assigning one of those numbers to each of the dice in sequence, thinking about rolling. Okay, so now we've got 5 factorial times 6 choose 5. What's 6 choose 5? 6, right? You're just picking which one to leave out. Yep. What's 6 times 5 factorial? 6 factorial, yes? Okay, so we've got 6 factorial ways of picking 5 of the 6 things and then putting them in some order. So these are the number of ways that we can satisfy the restriction that we get one of each number, that we don't get any repeats, that the 5 numbers are distinct. How many different things could happen in all? Well, there's 6 choices for what the first die gets, and 6 for what the second die gets, and 6 for what the third die gets, et cetera. And are all those, so there's 6 times 6 times 6 times 6 times 6 is 6 to the 5th different possibilities. Are those equally likely? Yeah, right? Because by assumption the die is fair, the die rolls are independent. There's no, every one of those 6 to the 5th possibilities is equally likely, so that's this over 6 to the 5th. And that gets rid of one of the 6's again, 5 factorial over 6 to the 4th, and you could work out what that is. Yep. Okay. This is probably the hardest question on the exam. He claims. I know, because I got, when I saw it come up, I got a little short of breath, going like, oh my God, am I going to mess this up in front of everybody? Yeah. Okay. Somebody want to run the number and see whether, whether we get it right? We could go a little bit further with the reduction, right? This is equal to 5 times 4 times 3 times 2 over 6 times 6 cubed. That cancels that. We now got 5 times 4 over 6 times 3 times 2 times 3 times 2. Those cancel that. And that ends up being 5 over 6 times 9 is 54. Is that right? OK, so 5 over 54 is just about 1/11, which ought to be about 9%, roughly. Is there a number here that's kind of like 9%? OK. All right. OK. Researchers studying the beliefs of, yes?
So, if the answer is closer to 9%, why was it like 9.2?
Oh, OK. So there's a couple things here. First of all, I am, as you know, a little off. And is closest to is literally meant as closest to. Some of the ways these answers are generated are that I take a range of values and I divide it into equal segments, and then I figure out which of those numbers is closest, and that becomes the right answer, so that the answer itself is not informative, right? Because that's just how I can make it that much nastier, right? No, it's just the answers. I mean, if it says is closest to, do not expect to see your answer there. Okay, just there will be some number that's closest. The other reason for saying is closest to is a hedge in case I actually programmed it incorrectly. So it could be that even if I intended there to be an exactly correct answer, I goofed, in which case there's still going to be a closest answer. Okay, so there's still one that I can grade after the fact and say, oh, that was the right answer for you because that was closest to what it should have been. Okay, all right. So it's hedging. Okay, so we want to know something about the beliefs of customers of a wireless telephone company. I want to know whether when people signed up for service, they believed that the recurring monthly charges were all they'd have to pay, or did they expect to pay taxes, surcharges, fees for text messages, usage above plan limits, et cetera, et cetera. How many of you pay your own cell phone bill? How many of you have a cell phone? Like everybody? Is there anyone who doesn't have a cell phone? Okay, this is kind of what I expected. All right, and of those of you who have a cell phone, how many pay for it yourselves as opposed to? Okay, a few. All right, so you have your own contract. You might or might not have read the fine print. You might or might not look at your bills when they arrive other than to look at what the total is that you owe. If you do look at your bills, if you did look at the fine print, you would see that there's a bunch of stuff you're responsible for over and above the $39.95 a month that they say that you're going to have to pay, right? There's taxes. Right. So question is, how are people aware of this or not? So during the period in question, the cell phone carrier had about 10 million subscribers. The researcher selects subscribers at random without replacement and calls them. And if she doesn't reach the person on the first attempt, she tries back up to twice more, different times of day. And if hasn't been able to reach them after the third attempt, goes on to the next person, keeps calling until she gets 400 subscribers in her survey. That required trying to reach 4,000 subscribers. Okay? Of the 400 whom she reaches, 20 did not expect to have to pay anything but the recurring monthly charge. Right? So what is the sample percentage of subscribers who didn't expect to have to pay anything but the recurrent monthly charge? It is the number who didn't expect divided by the sample size of 400. 20 over 400 is a lot like 2 over 40, which is a lot like 1 over 20, which is a lot like 5%. Yep. Okay, so the closest to 5% would be this, yes? Okay, don't expect the right answer, expect the closest answer, yes? All right, now if we want to make a confidence interval, oh boy, we got people upset now. Look, I mean, part of the reason for doing the homework the way it's done, where you get 5 chances, but you're not told which ones you missed until you've gone through it a few times, is to help you figure out what to be confident of in your own answers and what not to be confident of, to teach you, where to trust yourself and where to doubt yourself. This is the same kind of thing, right? I know the sample percentage. It's the number divided by the sample size, right? So you should be pretty confident that that answer is 20 divided by 400. And there is a closest thing. So you don't need the extra assistance of having the particular answer that matches yours there, right? He said, hopefully. Okay. All right, so we want to make a 95% confidence interval for the percentage of subscribers who didn't expect to pay anything. So the sample percentage is 5%. How much do we go up and down from 5%? Sorry? So for conservative 95% confidence interval, we would ordinarily use Chebyshev's inequality, right? And the upper bound on the SD of the box, assuming that the SD of the box is a half because this is a percentage. Except, what's the problem here? How many people did she contact? How many people did she try to contact? How many people did she actually contact? She tried to reach 4,000, reached 400. That's an enormous amount of non-response, right? This is not a simple random sample, right? Okay, the answer is E. Okay? This is like, what I really, really hope you get out of this class is, you know, when does the statistics not make sense at all, right? Because anybody can plug numbers into formulae. The question is, when is it right to use any formula, right? When is there no right answer? And what, you know, and if there is a right formula, you know, what is it? I'd love for you to be able to figure out for yourself, to derive the formula for yourself in situations where there is a right formula, and to have a really clear idea of when all bets are off. And this is a situation where essentially all bets are off because due to non-response bias, that answer could have been anywhere from, what if the other, 3,600 people had answered? If they had all said that they didn't expect to pay any extra charges, then what would the sample percentage have been? Right? It would have been 3,640 divided by 4,000. Right? It would have been very, very high. Suppose that all of them had said that they did expect to pay other charges. Then the sample percentage would have been 20 divided by 4,000, which would have been microscopic, right? Okay, so because of the non-response, you really have no idea what's going on here. And as the first question addressed, we don't have any reason to think that the non-responders are like the responders, nor that they're unlike the responders, but we also have reason to think that they're like the responders, right? Okay, so it's not fair to assume that they're the same. All right. This kind of question ought to be a piece of cake. Got 18 students, 7 of them are business majors, the rest are liberal arts majors. We take a simple random sample of size 5 and count the number of business majors. What is the distribution of the number of business majors in the sample? Simple random sample, we can think of the business majors as being labeled with 1s, and the other people, the liberal arts majors, as 0s. Nothing derogatory there. Okay, so there's 18 tickets in the box. 7 of the tickets are labeled 1. The other 11 tickets are labeled 0, right? Okay, you draw 5 tickets at random without replacement from the box. Sorry? It's hypergeometric, right? So the distribution of this is hypergeometric. What's the probability that the number is equal to 4? So what are the parameters of the hypergeometric distribution here? Good is equal to 7. N is equal to 18. N is equal to 5. And we're looking for the probability that X is equal to 4. Yep. Okay. So in order for X to be equal to 4, what has to happen when you reach in at random and pull things out? From the 7 business majors, you need to get 4. From the 11 liberal arts majors, you need to get 1. And what could have happened is that you could have gotten from the 18 any 5. Right? And all of these possibilities are equally likely, the denominator, because that's what we mean by a simple random sample. Right? So just a crunching of the numbers. He said, trying to sound convincing. Yeah. All right, what's the expected value of the number of business majors in the sample? Right, so the expected value of X is, just to try to review the heuristic behind this, you can think of how many people you get in the sample of size 5 as the sum of 5 things. The number you get the first time you reach in, number you get the second time, number you get the third time, fourth, and fifth. Right? There's sort of like 5 little indicator functions, one for each ticket you pull out. What's the probability that the first ticket you pull out is a 1? It corresponds to a business major. 7 over 18, right? The fraction of good tickets in the box, fraction of tickets labeled 1 in the box. Yep. So you've got the sum of 5 little things. Each of them has probability. Each of them has expected value 7 over 18. You get a sum of 5 of them, so it's 5 times that big. So again, if you remembered that the expected value of a hypergeometric is n, little n, times big G over big N, right? Or just that it's little n times what is like P for a binomial. P is the fraction of tickets labeled 1 in the box. That P is the same as 7 over 18, big G over big N. Okay? So the expected number is 5 times 7/18. This? There's 18 tickets in the box in all. We're going to pick 5 of them. Every single way of picking 5 of the 18 has the same probability because that's what we mean by a simple random sample. Okay, so of these possibilities, every one of these 18 choose 5 possibilities is equally likely. These are how many possibilities there are that correspond to getting 4 business majors. Okay. What's the standard error of a hypergeometric? Random variable. It's kind of like the binomial, except for the finite population correction because you're drawing without replacement, right? Okay, if this were just a binomial, sorry? You'd be, was that a question? No, that was a stretch. Okay. If this were a binomial, it would just be the square root of the number of draws times the SD of the box, right? What's the SD of the box? Okay, so we've got a 0, 1 box. We have a fraction P equals G over N equals 7 over 18 of tickets labeled 1. Right? SD of the box is the square root of P times 1 minus P, which is the square root of 7/18 times 11/18. Right? This is the SD of a 0, 1 box. If it has a fraction, any 0, 1 box, if it has a fraction, it's the box, right? We've got a box of tickets, and it has a fraction P. So there's n tickets in the box in all, right? A fraction P of them are labeled 1. A fraction 1 minus P of them are labeled 0. Right, so we're talking about the box. What is the SD of that box? SD of that box is the square root of P times 1 minus P. Okay? Now, what are we doing with that box? What we're doing with the box is different in different random variables, right? Okay, what we're doing with the box in this case is drawing 5 tickets without replacement at random. Okay, so for that, how is the standard error of the random variable related to the standard deviation of the box? Well, it's related through the finite population correction times the square root of n times the SD of the box. Okay? If we were drawing with replacement from the box, little n times, and counting how many tickets labeled 1 we got, then we wouldn't have f. Right? The standard error of a binomial is just the square root of n times the SD of the box. Square root of n times the square root of p times 1 minus p. Right? But the SD of the box itself. Now, if we didn't remember that this was the SD of a 0, 1 box. Sorry?
Was there an equation with the square root and the denominator?
For the sample mean.
Okay.
Yeah. We're talking about sums here. Remember the standard error of a sum tends to grow as the number of terms in the sum grows, right? It grows like the square root of n. The standard error of a mean tends to decrease as the number of draws grows. It decreases like the square root of n. This is the square root law. Okay? So we're talking about the sum, how many tickets we get labeled 1, not the fraction of tickets labeled 1 that we get in n draws. Right? So that standard error is going to tend to get bigger, except for the issue of f, which is going to eventually, right? If we took capital N tickets out of the box, f would be 0, and so the standard error would be 0. There's a trade-off. OK, do people remember where this comes from? Nope. Do you care? Yep. OK. I'll show you then. OK, we've got this list of numbers. It looks like 1, 1, 1, 1, 1, 0, 0, 0, 0, 0. There are n times p ones. There are n times 1 minus p zeros, right? OK, so the question is, what's the standard deviation of that list of numbers, right? That's the SD of the box. Huh? So how do we find the SD? Well, first we find the mean. Then we look at the sum of the squared deviations from the mean. We average that, and we take the square root of the result, right? It's the root mean squared deviation from the mean. Back when we were finding SDs of lists once upon a time. OK, so what's the mean of this list? Well, I get, if I added all these numbers together, what am I going to get? There's n numbers in all. I get a 1 for each 1. I get a 0 for each 0, right? If I add all these together, the sum is going to be n times p, right? It's going to be how many 1s there were. Now, that's the sum. What's the average? Right? Sum divided by how many there were. So the average of a 0, 1 box is the fraction of 1s in the box, p. So now I want to make the list of squared deviations from the mean so that I can take the sum of the squared deviations from the mean and divide that by n to get the mean of the squared deviations from the mean, the average. OK. And then take the square root of that. All right, so each one, what's the deviation of a ticket labeled 1 from the mean? Well, it's 1. The mean is p, right? And I want to square that deviation. So this 1 gives me a term 1 minus p squared. This one gives me another term 1 minus p squared. This one, right, et cetera. And then what do the zeros give me? There's going to be n times p of these. These are going to give me 0 minus p squared plus 0 minus p squared plus et cetera. And there's going to be n times 1 minus p of those, right? So what is the sum of the squares of the deviations from the mean? Well, it's 1 minus p squared, sorry, it's 1 minus p squared times that, there's that many of them, plus 0 minus p squared times that. There's that many of those. Let's go put this over here. All right, so I've got n times p times 1 minus p squared plus n times 1 minus p times 0 minus p squared is just p squared. Right? This is 0 minus p squared in some illegible handwriting. Right? And what am I going to do with these? I want to take the average of the squares. So I'm going to divide this by n to get the mean of the square deviations. That conveniently cancels that. Yes? And now, if we look at what's going on here, both terms have a factor of p, and both terms have a factor of 1 minus p. This one has an extra factor of 1 minus p. This one has an extra factor of p. So I can write this as p times 1 minus p times 1 minus p plus p. Everybody see that? P times 1 minus p times 1 minus p is p times 1 minus p squared. P times 1 minus p times p is 1 minus p times p squared. Same thing? OK. What's 1 minus p plus p? Okay, so this is p times 1 minus p. And now what's the last step in finding the standard deviation? Take the square root of it. Okay, so the standard deviation of a 0, 1 box is the square root of p times 1 minus p. Right? That's where that came from once upon a time. Okay, so we're back to finding the standard error of x. And we're drawing without replacement, so that introduces the finite population correction f. F is the square root of n minus n over n minus 1. And the standard error of this random variable is going to be f times square root of n times the square root of p times 1 minus p. What's p in this case? It's g over n, right? The fraction of tickets labeled 1 in the box. There's g in all. There's g labeled 1. There's n in all. And then times 1 minus g over n. Okay? So plugging into this would give the answer. Hypothesis testing, everybody's favorite. Okay, are we okay on the previous problem? All right. I've got some coin. I want to test the hypothesis that the coin is fair against the alternative hypothesis that it's biased in favor of heads. I'm proposing the following test. I'm going to toss the coin 7 times. I'm going to reject the null hypothesis that the coin is fair if I get 5 or more heads in the 7 tosses. Okay? If the null hypothesis is true, what is the probability distribution of the number of heads I get in those 7 tosses? Okay, it's binomial, right? It's like draws. If the coin is fair, it's as if I am drawing tickets with replacement from a 0, 1 box that has 1 ticket labeled 1, 1 ticket labeled 0. I'm drawing from that box a fixed number of times, 7, right? I'm drawing independently each time. So I'm looking at the number of tickets labeled 1 in a fixed number of independent draws from a 0, 1 box. That is the definition of a binomial, right? And the parameters of that are, of the binomial in this case, would be n equals 7, p equals 50%, a half. Okay? Okay, what is the significance level of this test? Right? What's significance level? What does it mean? Chance that we reject the null hypothesis when the null hypothesis is in fact true. Okay? So if the null hypothesis is in fact true, then the number of heads we get has a binomial distribution with parameters n equals 7 and p equals a half. And we reject the null hypothesis. This test says reject the null hypothesis if you get 5 or more heads in the 7 tosses. So we're going to reject the null if x is greater than or equal to 5, where x is the number of heads we get in the 7 tosses. So what we want to know is, what's the probability that x is greater than or equal to 5, given that x has a binomial distribution n equal 7, p equal a half distribution, right? So what is the probability that x is greater than or equal to 5 if x has a binomial distribution with n equals 7 and p equal a half? Well, it's the chance that you get 5 heads or 6 heads or 7 heads, right? That's how you get greater than or equal to 5. Okay, so that is then the sum from x equals 5 to 7 of, out of the 7 tosses in all, we need to get x heads. Yes? And the chance that that happens is we have chance a half for each of the heads. They're independent. And we have a chance a half for each of the tails, of which there have to be 7 minus x. And in fact, a half to the x times a half to the 7 minus x is just a half to the 7th, right? Because this coin's fair. Okay? So we have to add those three numbers together. There's some quizzical looks here. Is this, we don't like the summation sign. We want to work it out. Okay, so we got 7 choose 5 times a half to the 7th plus 7 choose 6 times a half to the 7th plus 7 choose 7 times a half to the 7th, right? That's what this is shorthand for. And what's 7 choose 5? What's a half to the 7th? Let's go. Half to the 5th is a 32nd. So we've got a 64th, 128th, 1 over 128. Yeah? Okay. So that's in all of these. Yeah? So what do we got? We've got 1 over 128 times a sum. 7 choose 5 is going to be 7 times 6. The rest of them get canceled by the 5 factorial. And then we have over 2 times 1. Okay. So that's 7 times 3, which is 21. Plus 7 choose 6 is 7. Plus 7 choose 7 is 1. Okay. So this is equal to 29 over 128. A little bit less than a quarter. Sorry? A little less than a quarter would probably be this answer. Yep. Woohoo. Okay. What's the power of the test against the alternative that the coin is biased, that the coin actually has a 60% chance of landing heads? We're finding the probability of exactly the same event, but under a different assumption. It's under the assumption that the coin has a 60% chance of landing heads, right? So this thing that we had up here is now 0.6 to the x, 0.4 to the 7 minus x, right? And we would modify this accordingly. These numbers would stay the same, but we wouldn't be multiplying them all by the same factor because now, since these two things aren't equal, this doesn't simplify quite as well. Okay? Bless you. All right. Do we want to work through the numbers, or this is just algebra? Yeah. Arithmetic. Yeah, it's still the chance that you reject. It's still the chance that you get 5 or more heads, but it's just the chance you get 5 or more heads for a different coin, right? Okay. Oh, multiple choice. These are evil. Oh, I hate these. These are like SAT questions. Yeah. Okay, you want to determine the effect of dietary fat intake on serum cholesterol. And the way I do it is take random samples of 1,000 adults from each of 80 countries and make a scatter plot of the average cholesterol level in each of those, for each of those groups of 1,000 people versus the average daily fat intake for each of those groups of 1,000 people. And the scatter plot turns out to be roughly football-shaped. The correlation between the average daily fat intake and the average serum cholesterol is 0.8. The scatter plot's football-shaped, so I compute a regression line. The line has slope 2. So 2 milligrams per deciliter of serum cholesterol per gram of fat intake per day. All right. So is it true that for the sample, people who consume 1 less gram of fat per day than average have a serum cholesterol level of about 2 milligrams per deciliter less than average? Right? This number is supposed to be the slope of the regression line. Right? Those numbers are the same. So I've got the scatter plot that has 80 points on it, and I compute the slope of the regression line, and as you go over by, so as you go down by 1 gram of fat per day, you go down by about 2 milligrams per deciliter of serum cholesterol. Okay, so is it true that in the sample, people who consume 1 gram of fat less per day on average have lower cholesterol in that amount? False. Okay. What's going on here? Okay, this is ecological correlation, right? The 80 points here are not people. Each of the points represents the average of 1,000 people. Right? Okay. Is the correlation coefficient likely to be higher for people or higher for averages of 1,000 people? Probably going to be higher for averages than for individuals. Sorry? No, it doesn't have anything to do with skewness. It has to do with more like variability across people. Tends to, like the example of education versus age. We did a scatter plot in the room of individuals' education versus age versus if we divided people into freshmen, sophomore, juniors, seniors. I mean, in the extreme limit, you'd have two groups of people. A straight line would fit perfectly, right? So it's going to tend to have lower correlation for individuals than for these groups across countries. Okay, so this is false. What about this? This is asking you about a causal relationship. It's saying that, is it the fat intake that is causing the cholesterol? So if you reduce the fat, will the cholesterol be reduced? Right? The scatter plot is saying, when you look at what people actually, what averages for people based on what they happened to do, higher fat had higher cholesterol. That's a different question from what happens if you intervene and reduce fat. Does that reduce cholesterol? Or if you increase fat, does that increase cholesterol? Right? This is about association. This is a question about causation. There is no intervention here. This is not an experiment. It's an observational study. You have no idea what would happen to these people if you changed their dietary intake. Okay? So this is false. You don't know what happens if you intervene. That make sense? Okay. Could be that, I mean, this is obviously silly, but it could be that well, there are other aspects to their diet or behavior or whatever that lead to having higher cholesterol. Could lifestyles are different in different countries, right? There's a lot of things that are different. Genetics are different in different countries. There are a lot of things that differ aside from how much fat you eat. Yep. Okay. All those things could contribute to cholesterol. All right. Because of ecological correlation, this study has little bearing on the effect of dietary fat serum on cholesterol for individuals. That's just rephrasing the reason why we said that 1 is false. Okay? So far, that's false, that's true. And then 4, because it's an observational study, you shouldn't infer a causal relationship. Yeah, that's true for the same reason that this is false. One of the same reasons. Okay? So we've got false, false, true, true. So 3 and 4 are true, 1 and 2 are false. Yep, okay. There's not a closest answer in this case. There's an actual answer. Yeah. Okay. In our legal system, person is innocent until proven guilty. So what is a type 1 error in our legal system? What's the null hypothesis? That you're innocent. And what does it mean to incorrectly reject the null hypothesis? It's to find them guilty, right? So a type 1 error is A. Okay, another of everybody's favorites. This is, because of the shrinkage of the page, this is not showing up so well. Let's, all right, what would you say that correlation coefficient is closest to? Negative 0.5, right? It's not 0. There's a downward trend. It's definitely negative, and it is not tight enough to be minus 0.95, anywhere near, OK? Not too hard. All right, these are straightforward, just like the midterm. So I'm not going to do this. This is just number crunching. But you should be able to find quartiles, percentiles, interquartile range, median, find out what the area of a bin in a histogram ought to be, so forth and so on, point of averages, calculate a correlation coefficient. This is all standard stuff. OK, what about this one, though? Problem 26. I have 8 observations. They're a random sample from a list of 51 numbers, right? I only gave you 8 data, but it came from 51, a list of size 51. We have the mean and the SD of that list. And this question says, what fraction of the numbers in the original list could be greater than or equal to some threshold? Well, what are your 2 possibilities here? First of all, can you have a negative number of people? No. OK, so we have some list of numbers. All the numbers, none of the numbers can be less than 0. Right? We know the mean of the list. So we could use Markov's inequality to get a bound on how many numbers could be really big. Yep. Well, we're also told the SD of the list. So we can get a bound on what fraction of the numbers, how many of the numbers are very far away from the mean of the list. We can use Chebyshev's inequality as well. You can compute them both and figure out which one gives you the sharper answer. Sharper, if you're trying to find an upper bound, means smaller or bigger? Smaller, right? More information. If a smaller lower bound is more information. A bigger lower bound is more information. You're limiting things to a smaller range. Okay, so take the sharpest answer you can get.
This is smaller, higher bound,
right? So we have 2 ways of getting an upper bound. Whichever one of those is smaller is better. Yeah. OK, we toss a fair coin 13 times independently. We have 2 random variables we're defining from that experiment. One of them is how many times the coin lands heads in the first 10, and the other is how many times the coin lands heads in the last 10. OK, 13 tosses in all. 10 and 10, first 10 and last 10 overlap, right? They overlap by 7. Yes? OK, are x and y independent random variables? No, right? If you know that x is, for the sake of argument, 10, that the coin landed heads all 10 times, do you know something about y now? You know that y has to be at least 7, right? No matter what happened. OK, so knowing the value of x tells you something about the value of y. If you know that x was 0, you know that y can't be any bigger than 3. Yep, they're informative with respect to each other. OK, here we've got an actual tabulated probability distribution. You're asked to find the expected value of x. How do you do that? What calculation do you do? The expected value is a weighted sum of the possible values, right? Where the weights are the probabilities. So we would, if we wanted to do this systematically, we could expand this table by another column and have a column that is x times the probability that x equals x. So the first entry in that would be 0.1111, right? The second entry would be 12 times 0.2963, et cetera. Then once we have those 5 numbers, how do we find the expected value? Just add them, right? Okay. What about the standard error? Okay, that's the expected value of another random variable. Which random variable? Well, sorry, it's the square root of the expected value of another random variable. Right? We'd find the expected value of x minus its expected value squared, right? So once we found the expected value of x, we could have another column here that is x minus the expected value of x quantity squared. And then we'd have another column that is that times the probability. We'd add those numbers together. And that would give us the expected value of x minus its expected value squared. To get the SE out of that, we take the square root when we're done. Okay, straightforward stuff, mechanical. All right. We have a box with 6 tickets labeled with those numbers. And we want to find, we're going to draw with replacement from the box. And in problem 30, we draw 200 times with replacement. And the question is, what's the chance that the sum of those 200 draws is between minus 57.15 and plus 114.31? All right, first of all, what's the average of that list? It's 0, right? OK, so that's not too hard. Yep, it's 0 because for every number, there's the negative of that number. Yes? All right. OK, so to use the normal approximation, we need to be able to convert these numbers, minus 57.15 and plus 114.31, into standard units. Right? How do we convert to standard units? We subtract the expected value, divide by the standard error. The expected value of the sum of 200 draws from that box is 200 times the average of the box, which is 200 times 0, which I'm pretty sure is 0. Okay? The standard error of 200 draws with replacement from the box is going to be the square root of 200 times the SD of the box. So we've got to find the SD of the box. Okay? What's the SD of the box? Well, we're going to get minus 6 minus 0 squared plus minus 3 minus 0 squared plus et cetera, right? Divided by, there's 6 numbers in the box in all, and then we're going to take the square root of that. Yep. OK, so we've got 36 from each of those two terms on the end, the minus 6 and the plus 6. So we've got 36 plus 9 plus 4 plus 4 plus 9 plus 36. That looks like 40 twice is 80 plus 18 is 98. Yep, OK. So we've got 98 divided by 6. Uh, 98 divided by 2 is 49, which is 7 squared, so that's not going to be divisible by 3. This is the square root of 49 over 3, which looks like 7 over the square root of 3. OK, somebody want to do that? All right, so the SE of the sum is going to be equal to the square root of 200 times 7 over the square root of 3. Square root of 200 looks like the square root of 2 times 10 times 7 divided by the square root of 3. Somebody have a number? 57.15? Gee, look at that. OK. All right, so this is one standard error below the expected value, right? 0 minus one standard error. The expected value is 0. And that looks a lot like 2 standard errors above the expected value. So what we're being asked to do, the normal approximation, once we've changed things to standard units, we're looking at the area under the normal curve from minus 1 to plus 2. Yep, that would be the normal approximation to that probability. OK, what's that? Well, the area between plus or minus 1 is 68%, roughly. So the area between minus 1 and 0 is half of 68%, right, which is 34%. So this part is 34%. And the area between plus or minus 2 is about 95%. Half of that is about 47.5%. OK? 47.5%. So what do we have? 81.5% approximately. Now we have a really difficult problem, which is what's closer to 81.5%, 74% or 97%? Okay. Did that make sense? You just don't like it? Okay. All right. All right. Suppose that we wanted to find the expected value of the sum of the squares on 200 random draws with replacement from the box. What do we do? How do we get there? The original box has the numbers -6, -3, -2, 2, 3, 6. If we're interested in the squares of the numbers on the tickets, we can just change this into drawing from a different box, where the labels on the tickets in the box are the squares of the labels on the tickets in this box. Right? So what would those be? We would have two tickets labeled 36. We would have two tickets labeled 9, two tickets labeled 4, right? And so the expected value of the sum of 200 draws from the box would be 200 times the average of the box. Just take the average of this box. Okay? This make sense to everybody? Okay. All right. We're out of time. I have office hours today. I'm going to schedule 2 office hours next week. I will send out an email letting you know when they're going to be. I think that they're probably going to be Wednesday around 1:15 and then Thursday at the usual time. Sorry? There's no formal review, but we're having office hours. I think the Student Learning Center probably will have a formal review. It's really been a delight to spend the semester with you guys. You've been a fabulous class. I'm going to miss you. I'll look forward to seeing you guys next week. Thanks.